you've heard the term speculative execution, so let's just talk a little bit about what that is. Speculative execution is a performance optimization technique used in modern CPUs to improve the efficiency of instruction execution. It involves predicting the path of a program's execution and executing instructions along that path before the actual outcome of a preceding instruction is known. This speculative work can then be used if the prediction is correct, reducing idle CPU time and speeding up overall execution. If the prediction is incorrect, the speculative results are discarded. Speculative execution works with branch prediction. CPUs use a branch predictor to guess the likely outcome of conditional instructions like if statements, if else, if this didn't do that, etc. For example, if a program has a conditional branch, the CPU predicts whether the branch will be taken or not and begins executing instructions in the predicted path. Instructions in the predicted path are executed speculatively. Results are stored in temporary buffers and are not committed to the CPU's state, like registers or memory, until the branch outcome is confirmed. When the CPU determines the actual outcome of the branch, like whether the condition was true or false, it checks the speculative execution's validity. If the prediction was correct, the speculatively executed results are committed to the CPU's state. If the prediction was wrong, the speculative results are discarded and the CPU resumes execution on the correct path. When the prediction is incorrect, the CPU flushes the incorrectly executed instructions and any changes they made. Execution is restarted from the correct branch or path. Speculative execution has benefits such as performance gains, allowing CPUs to make use of idle cycles and pipelines, increasing instruction throughput. And it helps with parallel execution by leveraging the pipeline and superscalar architecture. Multiple instructions can be processed simultaneously. Issues and drawbacks on speculative execution are the increased power consumption, as it consumes additional power because it processes instructions that may ultimately be discarded, and there's complexity. Implementing speculative execution requires sophisticated branch prediction algorithms and mechanisms to handle rollback and recovery. Spectre and Meltdown are these security vulnerabilities, side-channel attacks exploiting speculative execution to access sensitive data. They leverage the fact that speculative execution may leave traces in CPU caches, which attackers can analyze to infer information about other processes or memory. Mitigations for these vulnerabilities often involve disabling or limiting speculative execution features, leading to performance trade-offs. Speculative execution is a cornerstone of high-performance CPU design, but requires careful consideration of its trade-offs, particularly in security-sensitive environments.